this is a talk about a user interface to interpret code vulnerabilities. This was the subject of Tim Kane's senior design project, and Professor Diattore worked very closely with Tim on this project. At the same time, a graduate student, master's degree in computer science, Gordon Libb, was working on related subjects more closer to the background on Tim's project. And I have worked closely with Gordon on what he's doing for a master's degree. He has completed his second semester of research on this topic. Now, my role in the presentation this afternoon is simply to give you some background on the project and some background on the machine learning approach that we have used. Okay. MyTree is a private company that has, for on the order of 2 decades, provided a expert service to assist people in understanding their code vulnerabilities in terms of suggested or interpreted weaknesses in the codes that make them vulnerable. So throughout this little background presentation, I'm going to use the abbreviation CVEs. These are publicly reported code vulnerabilities. And of course, that is presented to MyTree with the hope that their experts can enlighten the code developers about CWEs, the code weaknesses that underlie the vulnerability. Well, the result, MyTree's involvement in this project over, as I said, about 2 decades, ultimately resulted in a national vulnerability database, which is managed by NIST, and it goes generally by the abbreviation NVD. So there are several links to the MyTree activity. The one I have here, called CVE-CVE, is primarily devoted to users who want to either download their CVE to MyTree or to get access to CVEs that are on file there. And my next slide is a little bit of what you learn by going to that CVE MyTree webpage. It starts out by saying that the CVE list is going to be it's going to be changed in this calendar year. I don't know exactly what the status of those changes are, but nevertheless, the mission of this particular part of MyTree CVE program: identify, define, and catalog publicly disclosed cybersecurity vulnerabilities. And out there on the page, when I went there, maybe 5 days ago, this particular CVE was up as the latest CVE to be submitted to the system. And of course, as soon as it's submitted to the system, it is given a CVE ID, and obviously a part of the CVE ID is the year in which the CVE was submitted to MyTree. And of course, that enables us to also break down the database by year, and that sometimes serves a useful purpose to say, look what the CVEs were, say 1999 to 2000, and look at what the CVEs have been since 2000. So that date's very helpful to us as part of the CVE ID. In this particular case, it says inappropriate implementation of web app installs in Google Chrome prior to this number. Now, I personally don't know the interpretation of that number, but I assume that somehow it's related to a date, allowed an attacker to convince a user to install a malicious web app to bypass install dialog via crafted HTML. And it gives a Chromium severity code, which in this case is medium. And it says, okay, this is our latest CVE. Now, would you like to just follow up and learn more about that CVE? So if you click on that particular link, you come to again, a description, a CVE ID, again, the description of that CVE ID, and some reference material that will help you distinguish this particular CVE from others that may, in fact, be very closely related to this one. So this is a short reference list then provided that will presumably give you a better insight into the meaning of this particular CVE. Then it says, if you want to learn more, go to the NVD database, and if you follow that link, you end up here, and it says that this CVE is awaiting analysis. And that was as of, as I say, 5 days ago when I started preparing this particular short introduction. So one of the main problems with the traditional system of dealing with CVEs, code vulnerabilities, is that expert assignments to CWEs generally was a slow process. And it is much more efficient to have an automated process to assign CWEs, to assign weaknesses to as an explanation for code vulnerabilities by some machine learning approach. And this is an active area of research at the present time, trying to get reliable and efficient methods to process the volume of CVEs that are being presented to the system at the present time. Now, one of those research activities led to this paper, V2W BERT, a framework for effective hierarchical multi-class classification of software vulnerabilities. And you can see that there's a fairly long list of authors there. And we have generally been in communication with these gentlemen. And our most immediate contact in this area is Mahantesh, since he works at P&L, and which is just down the road from WSU Tri-Cities. The bottom line of this particular direction of research is to do natural language processing on the CVE description, and like the one that I showed you in previous slides. This version of that particular machine learning process results in a vector with 768 components, if you wish, 768 attributes derived from natural language processing of the CVE description. And in general, many of them are labeled by some expert assigned CWE. Well, that was a sufficient database for Das et al. To undertake supervised machine learning to generate a model to predict CWEs from natural language processing of the CVE descriptions. And like most identification programs developed by deep learning methods, this model uses the softmax output, meaning that basically it returns a probability to associate the input CVE with each of 124 CWEs in the NVD system. Now, the MITRE system has more than 124 CWEs. In fact, it has more than 900 CWEs in their system. But most of these CWEs are very rare, and most were derived from research on code vulnerabilities rather than practical instances. And so NVD database was content with 124 of MITRE's CWEs to work on their association of CVEs with CWEs. And VW-BERT just took the 124 CWEs that are in the NVD system. Now, even among the 124 CWEs that are part of the NVD system, associating CVEs with CWEs, and used by VW-BERT in this supervised learning exercise, they are not uniformly distributed with respect to how often they're used as the CWE that is assigned to a particular CVE. And this little bar graph from VW-BERT shows how strongly peaked that distribution is towards 12 CWEs. Basically, the bar graph shows us that there are 12 CWEs in the NVD system, which historically have had more than 500 assignments per CVE. So we've had, let me say, 4 times 10 to the fourth cumulative CVEs in the system, and 12 of those CWEs have more than 500 CVEs per CWE. Then basically 15 more CWEs have 101 to 500 CVE assignments per CWE. Then there are 84 that have 1 to 100 CVEs per CWE, and then there are 13 more which have never had a assignment to a CVE. So as you can see, the use of CWEs in the mapping process of CVE to CWEs is strongly weighted towards less 50 or so CWEs. And the remaining CWEs in the system are what we call rare CWEs, and understanding those is an active part of research. Well, fortunately for our association with Mahantesh at P&L, we obtained a database that contained approximately 170,000 of these 768 component vectors from natural language processing of CVE. So that is to say, we obtained the database, which was the basis for the supervised machine learning carried out by Das et al. And each of the records that we received was labeled by the top 2 predictions of VW-BERT. As I said, the VW-BERT model is basically has a soft max output, and so the top 2 predictions represent those predictions which have the highest confidence level in the soft max methodology. Okay, that was what we needed in order to do unsupervised learning to cluster the vectors in the database using the SOM k-means method. Now, I want to emphasize that unsupervised learning does not use labels on the records. The labels on the records are completely ignored in the process of clustering the records themselves. However, when we come to the problem of interpreting the clusters that result from a given method, in general, the labels on the records are sort of the information that we have to do our first pass at interpreting the clusters. And that's the usual approach of unsupervised learning. Now, as I said, our labels are the predictions of the V2W BERT model. So you might be interested in knowing why would a person, if you have a supervised model that does some prediction of CWEs for a given CVE, why do we want clustering? Well, clustering has the advantage that it can give us a context for the predictions that V2W BERT makes. That is to say, it will associate the target CVE, the one that is the subject of our analysis, with additional CWEs that are most likely related in some way to the predictions of the V2W BERT model. And so it simply, it enhances the nature of the prediction of V2W BERT by giving the context of other CVEs that are probably related, are probably similar to the CVE of our current interest. And that's where we are in this project, is basically we've done the clustering and we're setting up a user interface that will return information about the clusters. And in the process, we're learning how to make the best use of our unsupervised learning results. Okay. Now, one interesting thing about the MITRE CWEs is that they have a hierarchical structure, which is again illustrated here by a small figure out of V2W BERT. And this particular hierarchical structure generally has 3 levels: level 1, level 2, and level 3, as illustrated here. And in going from the root CWE at the first level down to the leaves of the hierarchical structure at the 3rd level, generally speaking, we are moving from a weakness that's fairly general down to some very specific instances of where that weakness has occurred. And so presumably that then gets a weakness that's more specific to our particular target CVE. Now, Gordon is basically has done a lot of work here on searching the hierarchical structure, illustrating the hierarchical structure, relating hierarchical structures to our clusters, and he's gonna address that as soon as I'm finished here. And I'm really very close to being finished, because I just want to close by giving you a little bit of background about our clustering method, which is the application of self-organizing maps. This is basically a data compression approach. We've got a very large database, in the tens, in the order of 100,000 records. And SOM is a way to compress that into, and by finding a set of prototype vectors. These prototypes have exactly the same attribute, exactly the same meaning of the components of a prototype vector to a record in the database. But if you carefully select them, then they should represent a smaller set of vectors that more or less carry the full underlying the meaning of the full underlying database. And the process of finding these prototypes is, again, it's a deep learning, machine learning process. Basically, you have a grid and you keep presenting records from the underlying database to this grid, and by a fairly clever algorithm, these prototypes emerge. And we generally would seek to have at least a factor of 10 compression in any SOM application, which means, of course, if you have a database with 100,000 records, you would expect to have 10,000 prototypes typically. Now, the real value of the SOM data compression method is that the process of finding these prototypes topologically orders them on a two-dimensional array with prototypes that are similar grouped into clusters on this two-dimensional array. So, we typically, our history of data compression is using maps. Map is generally a two-dimensional display. And so we more or less understand this methodology as generating this two-dimensional array of prototypical vectors that can be organized into regions on the two-dimensional array with similar clusters, similar prototypes near each other on the grid. And that's what we call the map of the underlying data set that's provided by order of magnitude less, in an order of magnitude direct reduction in the size of the data set. Okay, now SOM maps are used for a variety of things. They can be used for regression, used for the classification, many applications of these maps. But we're using these maps to cluster the underlying data set. And how does that happen? Well, first of all, we have to quantify the clusters in the two-dimensional array, the prototypical vectors. And we apply k-means to do that. And k-means is a very commonly used clustering approach that basically, all you've got to do is specify how many clusters do you want, and here's an initial guess at where they're located, what their centroids are. If you do that, turn it over to k-means, it will fairly rapidly converge to a set of centroids that minimizes dispersion. Minimizes dispersion in the clusters, meaning that the clusters are tightly coupled clusters, and their centroids are widely separated. So that's the ideal situation in clustering. Tight clusters, widely separated. And k-means converges to that minimum dispersion, and you choose k to give the minimum dispersion of whatever you're clustering. Once we have defined the clusters of prototypes, then we go to a member of the underlying data set, and we ask which of the prototypes is most like this particular record in the database. And most like, generally defined as, in the Euclidean sense, it has the distance between the prototype and the vector of interest is smallest in the Euclidean sense. And we call that prototype the best matching unit of the underlying record in the data set. And all records for which the best matching unit is in the same cluster, they end up in a cluster in the underlying data set. So it's basically through this best matching unit concept and the clustering of prototypes within the 2D map that leads to clustering of the underlying database. Again, the number of clusters ultimately determined by the value of K used to cluster the prototypes by the K-means method. So that's probably more that I needed to say about the method. I hope you've at least got a feel for what the history of this project is and why we're doing it. And I guess I would be happy to answer anybody's questions if you have any.